I'm Ebenezer Scrooge. You've seen me do such fine quality epic chemistry educational videos, such as The Night Before Crystals and Electrons, Part 2, and I'm old, I forgot.
Okay, so we're going to be looking here at Chapter 6A, looking at the basics of bonding between the atoms, and you may notice your homework. That's it. That's it, that's it, that's it, that's it, that's it. Boom. Okay? Moving on. So, honors chemistry, that's all for you. This is just regular chem, but you define the words, and there's the H-chem. Let's go. Okay, let's do this. So there are laws of thermodynamics, and behind thermodynamics is how energy moves around, gets changed. But in the second law of thermodynamics, some people know that as entropy. The idea behind that is that things do tend to lose energy when they do. And when they lose energy, it also becomes more disordered. That's where we get the entropy idea from. Okay? So that being said, why atoms? They naturally want the low energy. Now, why is it? Well, for one thing, they lose energy. If you have less energy, you're a bit more stable. That's pretty much it. If you think about it, the little kid who's like, okay, very high energy compared to the kid who's more normal. The more normal energy level kid is more stable compared to, okay? There's a difference in there. So why do atoms bond? Because they lose the energy, but they also gain stability as a result. Now there is something called the octet rule. Now octet has a connection with the number 8. So what's up with that? Well, when the atom has its full valence shell of electrons. Wait a minute. What? Whoa, 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 whoa! Cut it, cut it! What are what's the valence shell? Outermost shell of the electrons. That's the key thing. Now, who cares? What difference does it make? Well, that's the thing. When that full valence shell is done, that's when the atom's really at its maximum stability. Now, how does that happen? Well, atoms give up electrons or atoms take electrons. It's one of the two. If they already have their octet full, they're going to sit there and do nothing. Like some of my students in class. Okay, I killed myself. All right. So atoms either give up electrons or atoms take electrons. And again, what's the point? Why do they bother to do that? To fill the atom's valence shell. That's the key. Because that is where the heart of chemistry is. That's it. Why do reactions happen? Atoms want to fill their valence shell. That's the idea. Okay? So what does that look like? Well, there's 3 types of chemical bonds that we have out there. One is the covalent. Now in the covalent, there's 2 kinds. There are 2 types. One is polar covalent, the other is nonpolar covalent. Yep. That's it. Polar covalent and nonpolar covalent. Then there's the second kind, which is ionic. Not ironic. That's an English term. Ionic. Yeah. And then the other one is metallic. Not necessarily. No. Metallic. So, covalent, ionic, and metallic. Inside of covalent, we have polar covalent and nonpolar covalent. Okay. So covalent bonds, how is it that they work? Well, here's the idea. Electrons are shared. Now they're either shared equally, which makes it nonpolar. Everything is even. Or they're shared unequally, and that's what makes them polar. Now you'd say, well, wait a minute, if they're sharing electrons, wouldn't everything be okay? It is okay. It's just like it's an unequal sharing of electrons or an equal sharing of electrons. And that does make a difference in how the atom behaves. No, I shouldn't say atom, because now it's a molecule. When you have 2 or more atoms connected together covalently, okay, if the electrons are shared equally, it's nonpolar. On the other hand, if it is not equal, then it's polar, and there is something to do with the polarity. There is a big deal about that. So if we look at nonpolar covalent bond example, we have two hydrogen atoms, they bond. It is nonpolar. Well, they're the exact same atom. Okay, so we know that the electrons are going to be shared equally. One hydrogen atom contributes an electron, that's an X, and the other is going to be the dot. So when they connect, okay, this is what it looks like. Now, in real life, this is what we picture the hydrogen atoms to be doing. That there's a little bit of a squishy there. You notice that there's a squishy there, and it kind of looks like a cell that divided. You know that very first cell division when the sperm and the ova get together to form that fertilized egg? Oh my gosh, we're going back to basic bio. Very true. We are. Now, that's nonpolar. Let's look at polar covalent bond example. So we have hydrogen and a fluorine atom that do this. Now, again, why? What's happening? The fluorine atom has a greater electron, that's what this arrow means, greater than electron negativity compared to the hydrogen atom. Okay, so in other words, the fluorine wants an electron badly. Okay, it will do whatever it takes to get that one electron. The hydrogen atom is, it could go either way. Okay? So when we look at this, notice this is not on your notes, this is a cartoon explaining, here's hydrogen, no, by electron, and notice that there's a partial positive charge here. That's where you got this delta symbol, and here's hydrogen with its plus, here's the electron, here's fluorine where it says, your electron will be mine. Notice you have a little delta symbol here and a minus sign. Well, what's going on? Well, look what's happening between the hydrogen and the fluorine. If you notice the electron, it's not even, is it? Well, the idea is that the electron's being shared more closely toward the fluorine. Why? Because it has a greater pull on it compared to the hydrogen. The hydrogen wants to hold on to it, but the fluorine, on the other hand, wants it badly. Okay? So, of course, if we look at something like the bromide ion, the chloride ion, the fluoride ion. Notice I didn't say bromine, chlorine, and fluorine. That is not the case anymore. What's happening is that they picked up an electron. The moment they picked up the electron, they became ides. That's why you got chloride, fluoride, okay? So, here's cesium, lithium, potassium, and rubidium, and they can't help themselves but be attracted, and therein lies the cartoon. So, is there a way to predict the bond type? Actually, there is. There is something called the electronegativity. How does the atom attract shared electrons? How badly does it do? If you have a high electronegativity, you really like electrons. You really have a high attraction for shared electrons. If you have a low electronegativity, then you're not as interested. So that's why we have a range of 0.7, that's francium, to 4.0, which is fluorine. Fluorine is very, very much interested. You'd say, but wait a minute, I thought chlorine would be more interested. Actually, chlorine's pretty much interested, but fluorine really is interested in getting those shared electrons. Yep, pretty much. So depending on the delta electronegativity charge, that's what En is for, the bonds will range from nonpolar to highly polar to ionic. So we can actually do that. Okay? And this is just a chart here that we go through. And you can see that, again, the numbers range. So here we have our low here about francium. It's like, here it's 0.7 or 0.8. And then here fluorine is about a 4.0. And if you notice on here, on the noble gases here, there's no electronegativity because they don't have an interest in attracting shared electrons. Because they're happy, they're stable, they don't want to do that. Okay? So when we look at the electronegativity difference and types of bonds, well, you know what? Depending on that electronegativity difference, The higher the electronegativity difference, the more ionic you're going to have and the less covalent it's going to be. When you have a very low electronegativity difference, that's when we talk about covalent nonpolar, where the electrons are shared equally. Now if it's like about 0.4, the electrons are shared unequally, so that means, yeah, they share, but you got an area of partial positive and an area of partial negative charges. Okay, and here ionic, you have a complete electron transfer. Okay, now with that, we're going to stop here for the purposes here.
Anyways, this is Ebenezer Scrooge. I'm signing off. Bah! Humbug!